We could do the same thing for the cosine function, except cosine has a different associated angle that we could find. 360 minus theta would give us an associated angle. Cosine is positive here and here. So those are the values that we might see. We have negative cosine in this quadrant and this one. So we did have values that we've calculated before, exact values up to 90 degrees. For cosine of 0, we ended up with 1. We did 45 degrees as well as 30 degrees. We had root 3 over 2 for 30 degrees. For our exact values, 60 was 1/2 and 90 was 0 for cosine. And we only went up to 90 degrees before. So these values are looking sort of familiar, but they're just in different, beside different angles here. 120 degrees, if we think about where 120 degrees is, an associated value with that, 120 would be over here. So if we imagine going in a negative 60 degree direction, we'd be able to have 120 degrees. Cosine is going to be negative in this quadrant though, and 60 degrees was 1/2, so this would be negative 1/2. 150 degrees, if we think about 150 degrees, we would almost be to 180, but we would come up here 30 degrees in a negative direction, negative rotation. So negative 30 degrees would be negative root 3 over 2. 180 degrees is going to be similar to 0, but in that quadrant we'd have negative 1. 210 degrees, I can start using my associated angle property here. 360 minus, so a second angle. If I had 360 minus 210, that gives me 150. So this is going to be the same value as 150 degrees. $240 degrees, I can do 360 minus 240, and I get 120. So this is going to be the same value as 120, negative 0.50. 270 degrees, I can just type my calculator, cos 270, and I'd get 0. Think about 270 being straight down this way, whereas 90 was up this way, and 90 degrees was 0, so 270 degrees is 0. 300, if I do 360 minus 300, I get 60. So we have an associated angle here. 300 degrees is going to be over in this quadrant. Cosine's positive here. So when I look at 300, 360 minus 300 is 60. So if I look at 60 degrees up here, that's a half. So I have 1/2, or 0.50 on your calculator. 330, 360 minus 330 is 30. Cosine's going to be positive. 30 was root 3 over 2, so we've got root 3 over 2 again. 0.87 is what you'd get on your calculator. I'm not going to 4 decimal places here just because that's pretty hard to graph anyway. So 2 decimal places works just fine. And then 360 degrees, we would be back to 1. So if we go to graph this, when we're starting at 0 degrees, we're actually up at 1. So this could be 1 and this could be negative 1. And the cosine function is actually starting here. Then we would head to 0.87 and then 0.5, 0, and then we're making our way to negative 0.5 and negative 0.87 and then negative 1, and then back up again for the cosine function. So our cosine function would look like that, and that would be one cycle going from 1 vertically all the way down to negative 1 and then back up to 1. The maximum value of the sine and cosine function, it's both 1. The minimum value, it does go down to negative 1. The domain, because in both directions, this function would continue on and on in both directions for both cosine theta and sine theta. We basically would have our domain and range You've kind of seen this before, x such that x is an element of all real numbers. We could write our domain in our notation like that, like you've seen before for quadratics. The range for both, we go as far as going vertically, we go down to -1 and up to +1 for both functions, sine and cosine. And then we have intercepts in different places. So the x-intercepts, or the intercepts for our angle measurement this time, where we hit for sine theta was -360, we'd hit at 0, 180, 360, and it's just shifted a little bit for the cosine function. The y-intercept here is 0, so sine theta started at 0 and cosine theta started at 1. So a last example here. Draw a sketch of y equals sine theta, locate 4 points having this coordinate, and write a general statement for all points having the y-coordinate √3/2 on a graph. So if we can imagine a sketch of this function, remember this is our 0.87. So they're asking, and it's positive, so where on this graph would our sine function hit a certain angle horizontally, but it's going to vertically be at 0.87. Our function started at 0, and at 90 we were already up at 1. And at 180, if we're drawing a sketch, we were back at 0. 270, we were at -1. So our sine function hit 0.5 and then 0.87 here and here. But then we didn't have any positive values anymore until after 360 degrees. So that this point occurs twice in 360 degrees. And when that occurs, we have the angle measurement would be 60 degrees, we get √3/2. And when we have 120 degrees, we have √3/2 for our value. So in another unit as well, we learned about coterminal angles. Coterminal angles occur when we add 360 degrees. So this question asked for 4 points. So even if we don't continue graphing this function, we know that it's going to repeat every 360 degrees. So I can say that coterminal angles, I just have to add 360 degrees. So if I look at 60 plus 360, I think that this pattern is going to hit 0.87 again at 420 degrees. And if I do 120 plus 360, I get 480. So I know we're going to be at 0.87 again at 480 degrees. From there, I could add another 360 to these, and I could get 2 more points, and then I could add 360 to that and get 2 more points. So we make up a general rule about this. Since we were at 0.87 twice in 360 degrees, I would have 2 general rules. Any angle could be 60 degrees plus 360k. How many rotations? We don't know. 1 rotation, k would be 1. If we did 2, it would be a 2, 360 times 2. I could keep doing this on and on. So that's what k represents there. K is an element of all integers, meaning k is just 1, 2, 3, or -1, -2. It could also be 0 because that would just be 60 degrees. And a second rule would be we take 120 and we add 360 to our angle a certain number of times, and k has to be an element of all integers.